Hello, my friends. Hello, my RF designer friends and colleagues, associates. Welcome back. This is Dr. Mohamed Nezami with another lecture on design of RF systems with modeling, baseband and RF modeling using SystemVue. Today, my friends, we are going to be discussing a design of a transceiver front end for a SATCOM application in the L-band. This is for the BGAN, which is the the broadband global network, or Inmarsat. And we're going to be designing a system that will interface with basically a digital card to implement a complete SATCOM terminal. So what I did is I put the design using the tool from Agilent, and we have the receive path in here and the transmit path in here. And the BGAN terminals, they share the same antenna, or aperture antenna. And so we have to have a diplexer, very high Q selective, pre-selective diplexer, which splits off between the receive and transmit, because as you know, they both have to be spectrally isolated, separated. So what I did here for simulation purposes is I split the receive and transmit into two pieces, so that this piece here doesn't exist. We usually connect this to here. So what I did is I took one receiver, removed the transmitter, and put a 50 ohm termination. And likewise, on the transmit side, I removed the receive path and put instead 50 ohm termination. So just so that we can simulate it. I got the components, all the components that I picked, and in a minute I'll go through the details. I have imported all the models using S parameters and the linear parameters, similar to what I've talked about in my previous discussion on designing low noise block for KU band. So let's start. Let's put a little theory, and then we'll come back to the simulations. Okay. So again, my name is Dr. Mohamed Nezami. I'm an independent RF circuit designer. A freelance designer right now. So you could contact me if you have any need for an RF designer anywhere from DC to 35 gigahertz. I can design it, simulate it, model, turn in the board laid out and bit of material, Gerber files, DXF files, everything that you need to actually build this thing. So, all right. So today we're going to talk about designing an NMR transceiver front end. This is a board level. The receive and transmit path simply, the specification that I have is like a little rough specification. So we're going to be doing close to 10 watts transmit signal. And then the receive path is like some 60 dB gain receiver. And the noise figure is below 2 dB. What else? The 1 dB compression point is somewhere in the minus 40 dBms. And we'll talk about that in a minute. Now, these terminals, they have tons and tons of companies that make these terminals, the Inmarsat terminals. And so they come in with variety of stuff like satellite on the move, parabola. They could come in like this, where they get installed on boats and vehicles. They can be like this, where they're fixed. They could be like this, where they're mobile. You move them. They could be like this, tacticals purposes. And there's plenty of companies, usually predominantly Hughes Network Systems and Cobham and Harris and L3 Harris and a whole bunch of companies makes these. Okay, so there's plenty of material if you like to learn on those, okay? But these are SATCOM terminals that are used for data and voice for missions like tactical missions and for ships and boats and travelers, explorers, oil rigs, and so forth. So here is the design that we're going to be designing today. And of course, now this design is the top level design. This is where you, if you're asked to do a design and you're at the top system level, where you have to identify the architecture, that's one, and then identify the pieces, the parts that you're going to use, okay? Now, this is not down to the schematic level. This is a stage that is way at the top. We do this, we system simulate it using SystemVue Pathwave baseband and RF system simulator. We verify it. And then we, after that, when we go ahead and start, of course, going into more details to up to the point where you get all the schematics ready and to start doing layout. And once you do the layout, then you come back to the RF designer and try to do what is called post layout verification from an RF EMI signal integrity point of view. That's where you take the board, import it into these design tools, and start cookie cutting pieces that are critical to this. So in today's design, I'm not using any discrete components, okay? We're gonna stick to mimics basically, okay? So everything is 50 ohm, okay? But it doesn't mean that when you have two pieces, let's say an amplifier and filter, each one is 50 ohm input out, and the return loss is somewhere, say, better than 10 dB. So it's not always as simple as just putting them together. You always, when you come to the schematics, you have to add, you have to tune, you have to optimize you have to add little inner stage tuning pieces. And so you end up with more to it than what I'm just going to show you here. But this is a critical part of that design. This is the architecture, the system. So this is what drives everything. This is what this is really the foundations. If these are wrong, everything else will be wrong. Okay. All right. So we've got, like I said today, we've got a modem. Okay, BGAN modem. Okay, the modem in this case is specified that I want the modulator is putting out minus 15 dBm. Okay, and then a demodulator that needs minus 45 dB. Okay, and then somehow we need to get to the point where we're taking a SATCOM signal, which is usually somewhere as low as minus 10 dBm. We want to take it down, amplify it, and filter it through a chain of components, okay, designed carefully, so that I could have minus 45 dBm with minimum noise figure introduced by this receive suction, okay, and an appropriate gain to put the signal from minus 120 dBm up to minus 45 dBm, okay? Likewise, on the other side, I have to take a low signal, which is minus 15 dBm. This is modulated signal, okay? And then I want to put that somewhere between 8 to 10 watts. So 38 to 40 dBms plus, of course, okay? Now, today's simulation, we're going to simulate and verify, pick the components and design this system in here. Perhaps maybe I will, next session, I will come back and actually look at putting a baseband section in here, generic baseband section, not necessarily a BGAN waveform. We could just put in a QPSK or a QAM and just observe the such parameters as the error vector magnitude, the spectral growth on the transmitter, and so forth. Okay, and you could even we could put a vector signal analyzer, okay, from the tool, and we could look at and monitor a whole bunch of other stuff as well. Okay, you could. I'm assuming that this can be directly digitized and this can be directly generated nowadays with the DACs and ADDs that we have at very high speed. But if you have a quadrature down converter, quadrature up converter, then you can introduce all the quadrature impairments, look at the effect of phase noise, and so forth. Of course, in here, we don't have any phase noise issues from this section because, well, we do have a little bit from the PA, but that's negligent right now. So it's direct, everything is direct. The same frequencies comes in, the same frequencies goes out. Okay, so the received frequencies are specified 1525 to 1559 megahertz, while the transmit frequencies are 1625 to 1660 megahertz. Okay, so there is a spacing between these two bands on the transmit and receive. Okay. All right, so I went ahead and looked at this and did my search, and here's basically the architecture, and here are the components that I picked, and these components are off the shelf, so you can purchase these using Mauser or DigiKey. These are basically, as you can see from the part numbers in here, these are the Hittite HMC series devices. They're from Analog Devices in the US, okay? These two filters, the receive filters, are from a company called CTS. They specialize in making ceramic filters. These filters are manufactured by at least 10 other companies as well. So you could go to any of those companies. But I just happen to have the S parameters for these filters in here, and I picked these. I'm not necessarily commercializing for no one here, but I'm just telling you that you could purchase these from various companies. Same thing for the active devices, the low noise amplifiers in here. We could have picked those from a whole bunch of other companies as well, but I just happened to pick this component. Of course, the model for these, I did generated a model based on the data that is included in the data sheets for all of these parts. The filters, I have the S parameter file, so I put that in. Now, the diplexer that separates the receive and transmit, this one is also from CTS, and the part number is here as well. So that's another thing. And in a minute, I'll show you in fact, let's go through some of the data sheets. Okay, so let's start out here. So this here is this is a filter. Let's look at the diplexer possibly first. Let's start with the diplexer. This is the diplexer, okay, and so basically it's specified with the transmit section, okay, 1525 to 1559, and the transmit section is here. I mean, this is the receive, and this is the transmit, okay. The device, they provide you with the footprint, and one of the most important things is that you copy the footprint as is for the BCB, otherwise you get a whole ton of issues. And this is the ceramic filter, basically. The antennas here, and on either side is the transmit and receive. Now, let's look on the receive side. We have the filter, the ceramic filter, which is right here. This is a ceramic filter that is from 1525 to 1559. Okay, so that's the filter right here. And again, they give you the suggested layout, so please make sure that you, very important that is laid correctly using that. We have an amplifiers. We have a bunch of amplifiers. Here's the, let's see, on the receive side. Okay, we have this, which is, this is the receive LNA. Noise figure is 0.75, okay. Gain is 19, okay. The voltage supplies are 3 to 5 anywhere, so, and then this is the data. Of course, in our band, we're talking this section in here, so everything in here applies to us, okay. So this is the data that I captured in the model, or the linearity. Well, they give you all of these so that when you generate the frequency dependent model, you use these graphs. What I do is I digitize them, store them in an Excel sheet, and load them into the simulator, okay? So the device is very simple to use, minimal parts, as you can see here. So you've got the 5 volts on the drain and on the gatings here, and just bypass cap on the input. The output is internally bypassed. There's a DC block. Okay, and there is a bias resistor in here that sets the current. And this bias resistor, of course, you have to follow what they have in here. Okay, so make sure that you follow the design rules that they have. All right. Now, on the transmit side, the devices, we start out with this at the modem, okay, which is a 17 dB gain driver amplifier, okay, which is not a driver, pre-driver, which is a TOW 342 package with a nice thermal heat. And I did go through this device. I've used the same device last time, if you recall, in the last video for the Illinois block. So they give you all the data sheet, all the performance curves are here, so you can go ahead and use these. And of course, the implementation of this is pretty straightforward. So you get the device and you have few sections that you have to follow here, and they give you all the dimensions for these microstrip lines for various, as you can see, lambda 1, lambda 2. So for every band, they give you that. But still though, what I do usually is take this into a ADS, and I put in this, and I put all these, and we run through the optimizer just to make sure, because these bands, what they give you here, like for instance, we don't see one for the 15 to 17, as you can see. So, which means that we can't really use any of these. You could use the closest, okay, somewhere between these two. However, you really need to verify it. And we have to do that in ADS. And on the coming videos that I will do, we will do that. We'll demonstrate how you do that. Now, the quickest way to do an ADS, of course, is you import the DXF file of the evaluation board, okay? And you just put a port for this device and stick the S parameters in there and start parameterizing these lengths in here, lambda 1, lambda 2, lambda 3, lambda 4, and these two capacitors, and run your optimizer. Of course, this inductor as well, because this really plays a role in there. Okay, so, and then the next device, which is a driver, is this device here, which is a 1/2 watt device, which is a nice device. I've used it in the past, 455 LP3E. Okay, and the design is straightforward. So just basically all you need to do is just make sure you come in 50 ohm, and again, you have lines in here that you have to optimize. So make sure that here's the physical length for these lines. And this circuit here is, let's see, for this band here, 1.7 to 1.85. So it might work with degrading a little bit, or again, you have to really optimize this on a simulator. So you copy all of these in the schematics and glue it all together, and then do the optimization. Now, finally, the 10-watt device that we have chosen for this design is this device here from Curvo, okay? And it's a GaN device. This is a GaN amplifier, GaN on silicon. Okay, so a real nice device, okay? So, and of course, this is a GaN amplifier, so it needs a special handling of biasing. You can't just put the negative and the positive in a random sequence. You have to have a soft start and soft shutdown, okay? So basically, this device has a large signal gain of 13 dB, small signal gain 18.5. Let's see, the cosecant current for the drain is 360 milliamps with 32 volts. That's the other thing. This works off 32 volts, okay? So you might want to be careful with that. And in the past, what I did before I used this device is I purchased this board from Curvo and experiment with this device up to the point where you're comfortable with it, because every time you blow one of these up, that's $50, $60. So it's preferable that you first accumulate experience based on using their evaluation board that comes in. It's better that way, okay? So this is the diagram of the circuit board. just copy it as is, okay? And then they give you, I believe there is a sequence for the bias sequence. Let's see, where is it? Let's see. If they still do here, I don't remember where is it. Okay, they might have it somewhere. Okay, so let's get back to finish the talk. So what we have here, so we have on the transmit side, we have the ADL device. This is from Analog Devices, okay? Originally, this is from Linear Technology, I think, before they purchased it. And then we have this device, which is same as we use on the transmit side. And then we have the driver, and then the final PA, and then we go through the diaphragm, okay? And then on the receive side, we have 3 identical devices and 2 filters, okay? Now, you might ask a question, say, why didn't I use the filter in here or in here? First of all, this diplexer itself is a filter for the receive path. So you really don't need to put a filter in here and end up with noise figure higher than you should, okay? We want to preserve the noise figure so that we can have at most, say, below 2 dBs, okay? So we hit an amplifier and then we immediately filter out, okay? And then we hit another amplifier, then we filter. And then finally we hit another filter, another amplifier, and then we don't do anything because in the demodulator, there is also a filter in there. So we save that right there, okay? Same thing in here. I didn't use a filter in here because I assume the modulator is an expensive equipment and it must have a clean spectrum when it comes out that you don't need a filter. We could have stuck a filter right here. By the way, they have ceramic filters that are specific for this band, for the BGAN, okay? So looking at the frequency response of the, let's look at these in the simulator. So you can see in the simulator, we have, this is the receive filter with this part number from the ceramic filter, which I did not use. Oh, no, I'm sorry, I did use, of course, that one, but I was thinking the transmit filter. This is a transmit filter, which I did not use at all, okay? But it is available if you want to use it, okay? So this is the diplexer. So with both the receive band and the transmit band. And you can see the loss, this one is really optimized for the receive path. So we will start a few tenths of a dB, I mean 7/10 of a dB, 8/10 of a dB to 1 and a little bit dBs and insertion loss, while the transmit side has about 1.2, 1.4 dB, okay? We have this low pass filter that I did not utilize anyway, so this was just as a reference there. Okay, so let's get back. So we covered the diplexer filter, how the spectrum response. Then we go through the whole chain in here. The first simulation we did is we swept in frequency from the receive from the antenna to the demodulator, and this is the response I got right now from this chain, okay? With these 2 filters, the diplexer, and the 3 amplifiers. And the gain right now is 60 dB, which is pretty good. That's exactly what I want. Everything's flat, it's nice, and everything, hopefully, when you lay this out and you interconnect it, it will preserve, you would preserve the flatness of the passband. On the transmit side, we start out from -15 and go up to 38 dBm or 40 dBm. And so this is what I've got. And you can see that on the transmit path, this filter, the way the diplexer was designed in such a way that it would have a steep, very high loss in the receive region, is because you can imagine when you have plus 40 dBm, you need to get down to this level. I mean, this is 60 and this is like -4. So this is 70, 80 dB below the transmit band, and that's what you want. The overall gain for the transmit side is around 58 dBs, okay? Now, what I did is I swapped the transmitter from the modulator to the antenna, and this is the curve that I got. Okay, so basically it saturates at 38.62. Okay, so it's just 7 watt, a little bit above 7 watts, 7.25 watts. Okay, and that's because the device is 10 watts, but I did not drive it to fully 10 watts, and there was a little bit of losses in the front end, as you can imagine, from the diplexer. So, okay. So the device starts compressing close to like 27, 28 dBm. Okay, so on the receive side, also I swapped it from the antenna to the demodulator, and I swapped the signal from -100 to -30, and you can see that it's very linear up to the point where it starts getting close to -44 dBm. Okay, and of course the SATCOM signals, I don't know how you would get -44 dBm unless you're up there with in a spacecraft. So this is very good. So you're always going to be operating in this region here. So this is nice. Everything is nice. Of course, the saturation level is 20 dBm. So that's really what the saturation level of the actual LNA device. If you look at this device here, where is it? No, not this device. Where is the LNA? Okay. Okay, here's the LNA. So if we look at the device in here, the 1 dB compression point, the output 1 dB compression point for us is like 19 dBm, okay, for that whole thing. So from the simulations, that's what we have is 20 dBm. Now, you might want to make sure that that 20 dBm is acceptable to the demodulator, because a lot of times these demodulators, you want to make sure that you don't want to damage it or overdrive it. So this is just in case if you're not going to get any SATCOM signal that will result in 20 dBm, but you might get an oscillation, you might get some kind of interference that leaks in the lab, and then it might very easy to put you at 20 dBm at the demodulator. So you'll make sure that that level. If not, then you need to change this device possibly. Okay, so let's look at the budget link throughout the receive path. So we start out right here at the, this is where the diplexer all the way to the demodulator, and we can track the progression of the, basically we have the desired channel power, okay, which is the received signal. We have the cumulative noise figure, and we have the cumulative gain, RF gain, and then we have the cumulative input 1 dB compression point. And you can see that the system starts out nicely, and there's nothing unusual. Everything is smooth, and we do get the output when we have -110 dBm, which is -46 dBm. Okay, that's the minimum that it was designed for. The overall noise figure is 1.654 dBs, which is pretty good for this application. We're happy with that. Now, we did the same thing for the transmit side. We swept the transmitter from these devices up to the diplexer, and that's where it started out -15 dBm at this point here. And you can see that we progressed up and built the signal until we get to the final at the antenna, 38.6 dBm. So everything looks nice. So, and this is what we've got here. So we come in here and let's look at the basically the first one is the receive path. So this is the receive gains. You can see that we got 63 some dB gains. The budget link on the receive side, this is what we have. So we start out with the signals off nicely. Oh, this one's something that I didn't talk about, but this is basically I'm sweeping the front end for compression at the outer band areas, but we can talk about that later. Okay, so this is nice. On the transmit side, we can go to transmit. We got 58.78 overall gain. This is overlapping both the transmit and receive, and you can see this one is 58.59 dB, and this one is 63 dBs. Okay, the TX overall budget, and same thing on the sweep. So there you go, ladies and gentlemen, that we have it now. So now you might say, okay, well, this is nice and cool. So what we do next is we grab the schematics for all of these and we start building this thing in schematics. You could go to ADS and start building there and then just to verify the whole thing, EM it. But that's in the, we're going to do that hopefully in the next, some coming up videos, okay? So again, so what we did is we designed today a system architecture for an Inmarsat transceiver front end, okay? We took this system here where we drew it by hand, the block diagram, and we realized that with real parts from manufacturers that we can buy off distributors like DigiKey and Mauser. We looked at analysis for linear and nonlinear analysis for the chain. We could do more analysis, but this is good enough for right now. This is proven. This method is proven that you can actually go ahead and start putting schematics together. So, ladies and gentlemen, I thank you very much for watching my video. You can, if you're interested more, you can register for my training sessions that are coming up. We have one on ANSYS, HFSS. You can go to my video channel in here, YouTube channel, and you can watch the videos that I did, 30 or so videos on material that is covered in this workshop, which is 3 days. I also have another 2 workshops, one on the SystemVue design package, which is what we just did today. If you like that type of work and you don't want to get involved at the circuit level, you can come into that course and we stop it at the block level diagrams and don't go further. But if you want to if you're interested in doing the other part of it, go down to realize the actual board, then you need to attend this session in here. And both sessions are held in Jerash, Jordan. I operate out of Jordan, so things are cheaper. My prices are always $1,000 for each attendee. That includes your hotel room, your boards, your meals and field and tourist trips around the area. Okay, so contact me on this email if you like to attend any of these. So, ladies and gentlemen, we will have more SystemVue presentations coming up. Now, somebody might ask, can you actually put this thing together from zero up? And I again, like these people were writing me when I was doing the ANSYS HFSS, these presentations are on the concept of RF design, not how to use the tool, okay? Now, it's how to make you aware that what you can do with the tool, but I'm not going to sit down and make videos on there's plenty of videos on that from the manufacturers, both of these softwares. You can go to them. They have tutorials, they have training shops, and there's plenty of that stuff loaded on YouTube, okay? Well, again, I do thank you very much for attending. I will see you in the next training session. Thank you very much and have a great day, night, whatever time it is in your area.